Hello everyone, I hope you're doing well today. Today we're going to start talking about the end behavior of polynomials. What that means is when we look at the graph, it's the directions that the arrows are pointing in, either up towards positive infinity or down towards negative infinity. But before we get into that, we need to define a few terms. Our first definition is a degree of a term, which is just the sum of the exponents. Looking at our three examples here, we're only going to look at the exponents of the variables. So looking at our first term, 3x to the fifth, the only exponent is 5, therefore the degree is 5. Looking at the second example, 2a to the third b, our degree would be 4. Our variable a has a degree of 3, and the b has an understood exponent of 1. Adding together, we get a total degree of 4. And looking at our final example, 4 squared, f to the third, g to the fifth, h to the second. It doesn't matter that the 4 has an exponent of 2 because we're only going to look at the exponents of the variables. So to get my degree for the entire term, I would add 3, 5, and 2 to get a degree of 10. Take a moment to pause this video and write down the definition and examples. The next term we need to define is the degree of a polynomial. The degree of a polynomial is the highest degree of all of the monomial terms, or each individual term. Let's take a look at a few examples. Looking at the equation, y equals 2x to the third minus 5x to the sixth plus 3x squared, we have three individual terms. The first term has a degree of 3. The second term has a degree of 6. And the final term has a degree of 2. Since 6 is the highest, 6 is the degree of the polynomial. Looking at our second example, p of x equals 3x to the fourth plus 4x squared minus 5 plus 8x to the seventh. We have a degree of 4 for our first term, 2 for the second, 0 for the third since there are no variables, and 7 for our final term. The highest degree of all of the individual terms is 7, therefore 7 is the degree of the polynomial. Please take a moment to pause this video and record the definition and examples. The next term that we will define is the standard form of a polynomial, which is a polynomial written with its terms in descending order of degree. So looking at the two examples that we had before, looking at the equation y equals 2x to the third minus 5x to the sixth plus 3x squared, we determined that the degree was 6. So we're going to rewrite our equation, but we're going to start off by writing the term with the highest degree first. So it'd be y equals negative 5x to the sixth. Looking at our remaining two terms, we have a degree of 3 and 2. We would write the term with the degree of 3 first because we're going in descending order. So it'd be plus 2x to the third plus 3x squared. Looking at our other example, with p of x equals 3x to the fourth plus 4x squared minus 5 plus 8x to the seventh, we determined that the degree was 7. So when we rewrite our function, we're going to start off with our term 8x to the seventh first. The next highest degree is 4, so we would then write plus 3x to the fourth. After the 4, the next highest degree is 2, so we'd have plus 4x squared. And the lowest degree is 0, so we would end with our constant term, negative 5 at the end. Now both of these polynomials are written in standard form. Take a moment to pause this video, write down the definition and the examples. The final term that we need to define is the leading coefficient, which is just the number in front, or the coefficient, of the term with the highest degree. So now that both of these polynomials are written in standard form, it's really simple to identify the leading coefficient. It would just be the number in front of the first term when it's written in standard form. If not, identify the term with the highest degree and then find the number in front of it. So looking at the first example, the number in front of our term with the highest degree is -5, so our leading coefficient is -5. In the second example, our highest degree is 7, the number in front of that term is 8, therefore 8 is the leading coefficient. Take a moment to pause this video and write down the definition and examples. Now before we discuss these 4 graphs, I'd like you to take just a moment to pause the video and write down any observations you have about each of the equations and or graphs. Okay, now let's start talking about what you might have observed. Looking at our first graph, y equals -x squared, you'd notice that it has a degree of 2. Looking at the one directly below it, you'd notice a degree of 4. Looking at the one in the top right, we have a degree of 2, and in the bottom right, we have a degree of 6. So all of the functions have an even degree. Now, if we had taken a moment to draw in our arrows on the graphs, you might have observed that the arrows were always pointing in the same direction. This will be true for any even degree function. Now, if you look at the 2 graphs on the left-hand side, you'll notice that they're both pointing down towards -infinity. That's true because of a negative leading coefficient. So whenever there's a negative leading coefficient, our graph will point down towards -infinity. And if we look at our 2 graphs on the right-hand side, we'll notice the leading coefficients were 3 and 2, so they were both positive. So if we have a positive leading coefficient, it'll point up towards positive infinity. Please take a moment to pause this video, draw sketches of the graphs and the equations, and record down the 4 observations that we have made. Now I'd again like you to take a moment to pause the video and jot down just any observations that you have about the equations or graphs. Well, if we look at our equations, y equals x, y equals -x cubed, y equals 3x to the 5th minus 2x to the 3rd plus 1, and y equals -2x to the 7th minus 4x to the 3rd plus x, you should have noticed that all of the degrees of these functions are odd. If you look at the graphs, they're either increasing or decreasing. The arrows, if we put arrows on the ends of the graphs, they would be pointing in opposite directions. And we can look a little bit further and make observations as well about their coefficients. So if we look at the first 2 graphs on the left-hand side, they have positive leading coefficients and the graphs are increasing. What I mean by increasing is that if we read the graph like a book from left to right, it is going up. So if we have a positive leading coefficient of an odd function, our graph is increasing. So one arrow is pointing up towards positive infinity, and the other is pointing down towards -infinity. And looking at our 2 graphs on the right-hand side, we notice that the leading coefficients are -1 and -2. If I have a negative leading coefficient, the graphs are decreasing, and that means again, one arrow is pointing up towards positive infinity, the other is pointing towards negative infinity. Take a moment to pause the video and record our observations. So using the observations we've made, we can classify our end behavior using this table here. So you'll notice in the table we have odd degree and even degree end behavior. And we also have information about the leading coefficient. When it says that a is greater than 0, that means it's referring to a positive leading coefficient. When a is less than 0, it's referring to a negative leading coefficient. If you notice with the even degrees, they are both either pointing up or down. And the end behavior for an even degree function with a positive leading coefficient, as our x values are decreasing towards negative infinity, as they're getting really small going in this direction here, our y values are going up towards positive infinity. And also, as our x values are getting really large going out this direction, our y values are also going up towards positive infinity. And that can be defined in the statement here and here. And then with a negative leading coefficient, as our x's are getting really small, so are our y values. So as x is approaching negative infinity, our y values are also approaching negative infinity. As our x values are getting really large, our y values are getting really small. So as x is approaching positive infinity, y is approaching negative infinity. Now going back to the other part of our table with an odd degree. As our x's are getting really large and going out towards positive infinity, our y values are also going towards positive infinity. As our x values are getting really small and going out towards negative infinity, our y values are also getting small and going towards negative infinity. So as x goes to negative infinity, y goes to negative infinity. And finally, for a odd degree with a negative leading coefficient, as our x's are getting really small, our y values are going up. The arrow's pointing up. So as x is going to negative infinity, y is approaching positive infinity. As our x's are getting really large, our y values are getting really small. Our arrow's pointing down. That means as our x value is approaching positive infinity, our y value is approaching negative infinity. Please take a moment to record this table as a summary for your notes, and I will see you shortly in the Zoom meeting.